Okay, in the notes that we're going to go through now, I want to continue thinking about systems of linear differential equations with constant coefficients. So here's an example that we were working with last time where x and y are denoting the number of bacteria in two different colonies, and they're changing over time. And so if their differential equation were given by this system over here, in the last set of notes, we talked about how we can set up a matrix equation, find eigenvalues of the corresponding matrix, which in this case were 3 and minus 2, and that would tell me what the solutions for x and y should look like. And then by substituting what we know about the solutions of x and y into, say, one of these differential equations, we can then figure out how the coefficients depend on each other in the two general solutions. So last set of notes, we derived this general solution for this system of differential equations. And so what I want to think about next is, well, these are general solutions, so what happens if we throw in some initial conditions? So for example, if I know that at time 0, colony X has, say, 300 bacteria and colony Y has no bacteria, what would we expect to happen? What would the solution to the initial value problem be? So let's plug in these conditions and solve for C1 and C2. So we're not going to change how we would approach that. So for example, if I start with the equation for y and plugging 0 into that equation for y, we would get minus 1/2 C2 is equal to, well, the initial condition was 0. So this would tell us that coefficient C2 is 0. Then we can use that information along with the initial condition for x to figure out what C1 is. So at time 0, we know that colony X is going to have C1 plus C2. And now we can plug in 0 for the value of C2, and we could set that equal to our initial value for X, which is 3. And from this, we can see that C1 needs to equal 3. And once we've got these values for C1 and C2, we now can express our general solutions more specifically with the solution to the initial value problem. So X would look like 3 e to the 3t, and y of t would just be 0, right? And so if we start with 0 amount of y, we're going to always have 0 amounts of y. And so now let's see what this would look like in the phase plane. So if I wanted to sketch this corresponding solution in the phase plane, we have x over here. Let's say we've got y over here, and we're starting off at initial condition corresponding to 3, 0. Okay, so this is our location at time 0. And now as time goes on, well, first of all, y isn't going to change. Y is always going to be 0. So the first thing we can note is that the solution is going to remain on the x-axis. So it's going to remain on the line y is equal to 0. But it can go in two directions. So maybe we head this way. It's possible we head that way. To see which direction we head in, we can look at the solution for x. And for this, we can see that as t goes to infinity, x of t is going to head towards infinity. So the solutions are going to head out in this direction over here. So I'm just going to put a little arrow along there. So if we start at 3, 0, we know that as time goes on, that solution is just going to head to the right along the x-axis. Okay, so in part B, let's take a look at a similar situation, but now we're going to say at time 0, we're going to start at 2 minus 1. So let's kind of ignore the fact that we couldn't have a negative amount of y. So let's say here we are at time 0. let's figure out for these initial conditions what the coefficients C1 and C2 would need to be. So again, if we start with the equation for y to begin with, so at time 0, y of 0, when I plug 0 into that, I'm going to get minus 1/2 C2. And we're told that the initial condition for y is that y is equal to minus 1. So solving that for C2 would tell us that C2 is therefore equal to 2. And now, using the initial condition for x, when I plug 0 into that equation, I would get C1 plus C2. And now we know that C2 is equal to 2. And we're told that at time 0, x is equal to 2. So this would tell me that in this example, C2 is equal to 2 and C1 is equal to 0. So therefore, our solution for x of t is going to be 0 C1. C1 is equal to 0, so that first part is going to be 0, and then we've got 2 times e to the minus 2t, and our solution for y of t would look like, we'll see 2 is equal to 2, so that's going to give me minus e to the minus 2t. And maybe it's not as clear what's kind of special about this solution, but if we start at the point 2 minus 1 at time 0, then what we can see is that the ratio of our x and y values, if I take y of t and divide it by x of t, then I'm getting e to the minus 2t all over 2e to the minus 2t. So in other words, this ratio is always equal to minus 1/2. So the ratio of x to y is going to always stay the same. And so another way to think about that graphically is that it's always going to be the case that these solutions are going to remain on the line y is equal to minus 1/2 x. So in this case, we're starting off at the point, say, 2 minus 1. I'm just going to approximate it as being someplace over here. It sits on this line, y is equal to minus 1/2 x. And what we just observed is that if I start on 2 minus 1, that our solutions are always going to remain on that line. So that's the first kind of important observation, is that I know my solution is going to sit on this line through the origin. And secondly, we might want to ask, well, what happens as now time goes to infinity, as time goes on? And what we can see in this solution is that as time goes to infinity, x is going to head to 0, and y is also going to head to 0 because we have negative powers in the exponent. So that means our solution here that we started at the point 2 minus 1 is actually going to head in back towards the equilibrium at 0, 0. Okay, so we're going to blow up the dynamics, this little graph that we have up here on the next slide to kind of summarize this. But before we turn to the next slide, I just want to note that, okay, what have we been doing? We've been using some initial conditions. And what we saw is that here are two really special initial conditions in the sense that if I start at this point 3, 0, I'm going to always remain on this line y equals 0, and we know exactly what direction we're going to move in. If I start at any point on the line y is equal to minus 1/2 x, what we've shown is that the solutions are going to always stay on that line, and in this case, they're moving in towards the origin. So let's use what we know about these two special solutions to get an idea of what all of the solutions might look like in the phase plane.